V multiplied by E. So this is the V multiplied by E. And then plus by F prime H over 2. Okay. So if I tidy things up, so note that F is equal to F prime. So therefore, VE is equal to minus, right? Minus FH, right? FH, yeah, is equal to minus, and E is equal to minus FH over V, right? So over here, this is the magnitude of the shear center. The fact that it's minus is because it's going towards the what? It's going towards the left. Okay. So after here, after you know what is your E value, okay. So with the shear center, okay, the structure will deform without twist, and then shear stress is equal to VQ over IT is valid. Okay. So only if you apply the shear force, okay, at a certain distance E away, you eliminate the twist, then you can use VQ over IT. Okay, so what we are trying to do is just to get rid of the what? Of the twisting. Okay. So now I'm going to do an example. This is not so difficult. It's just an explanation to tell to the theory. It sounds really hard. Okay, it's like, oh, here we go again. No, okay, it's not that bad. Okay, so I'm going to do an example for you. Two examples. Okay, so I'm going to do two examples for you. So this is example number 1. And I want you to pay attention to how things are calculated, because it's a very unique approach to calculate second moment of area with this topic. Okay, I want you to focus on that. Okay, so we're going to look at this example over here. Let me copy first. Again, we're going to apply everything we have learned. Okay, the 6 rules now, everything. Okay, right. So determine. So this question determine the location of the shear center O of a thin wall beam. Okay, of uniform thickness having the cross section show. Okay, so we're trying to find the shear center E. Okay, we're going to find the shear center E. Okay, so this is what we are trying to find. Okay, so we have all those respective distance. Okay, so all this distance over here you will see is all relative to the center line, right? If you look at the distance from A to A, the A, it stops down here. Oh, let me right, it stops down here, so it is at the center of, so if this is T, right, where it stops from here to here is T over 2. I just want you all to be sure about that. Okay, so it is at the center line. Okay, if you want to call it, you call it the center line. Okay, so we're going to find what is find the shear center. Okay, so let me look at the solution procedure first. Okay, let's look at the solution procedure. Okay, so solution procedure. Okay, so we have to find what is our forces, right? So we have to find what is our forces. So forces is equal to, you integrate tau and then dA. Okay, so you have seen this before. We have just written this out. Okay, we have just written this out. Right. So we know that this is also the area, cross-section area. Okay. So we have to now, before we do anything, all right, we have to find the force first. In order to find the force, right, in order to find the force, we need to relate with the shear stress is equal to VQ over IT. Right? You need that. Okay. Right? And then before you can find what is, so you also need to what? Find I first. Right? You have to find your I first and determine Q at different section. And then finally, okay, so finally, right, finally, after we know all this and after we have find F, then we're going to take moment about point C. Okay, so this is, I'm going to call this point C. Okay, we're going to take the moment about point C. All right, about point C to find the distance E. Okay, we're going to find the distance E. Okay, so let's do the first thing. So the shear force is, I'm going to draw the transformation. So this is Y and Z. Okay, so we have a shear force acting down here, Py. And this is unsymmetrical loading because the stiffness is different, right? Right, the stiffness on the left hand side and the right hand side of the structures are not the same. Okay, they are not the same. Okay, so now we have to determine. So the first thing we have to do is we're going to determine IZZ first. Okay, so we're going to determine. Yeah, I'm going to copy the diagram. You're going to determine IZZ. Okay, that's what we want to find out here. Okay, so IZZ is equal to twice of IAB plus by twice of IBD plus by IDE, right? Because the top and bottom are the same. Okay, so AB and FG are the same. BD and EF are the same geometry, and DE is alone, right? So I'm going to write note that IAB is equal to IFG and IBD is equal to IEF. Okay, so we have that relationship. So we're going to find IZZ first. All right. So because writing our axis again, so this is Z, this is Y. So if that's the case, parallel to the axis is the width, perpendicular to the axis is the depth. Right. So IZZ for IAB, so twice. So the width, I'm going to call it T, okay, or thickness, okay. So all have even thickness, okay. So width T multiplied by depth A cube over 12 plus by T multiplied by A, okay, T multiplied by A, or yeah, T multiplied by A, and then multiply by A plus by A over 2, okay, plus by A over 2, and the whole thing squared. Okay, so that is for IAB. Okay, then plus by twice again. The width now is 2A multiplied by T cube. Okay, T cube plus by 2A multiplied by T multiplied by A squared. Okay, and the last one plus by the width is T, the depth is 2A cube over 12. You don't need to plus the area offset because the centroid, the individual centroid and the global centroid are the same. Or if you want to do this, you will have the width multiplied by 2A multiplied by 0 to power of squared. Okay, just to write it down for you. Okay. So now we are going to remove the brackets or expand the term any way you want to see it. So IZZ is equal to 2, okay, twice, right, TA cube over 12 plus by 3 over 2, 9 over 4, so 9 over 4, so 3 over 2, so 9 over 4, right, TA cube, then plus by, oh, I forget to divide by 12 over here, do apologize, twice of AT cube over 6, right, then plus by 2 T8 cube, right, and then plus by what, plus by 2 power 3 is 8 TA cube, TA cube over 12. Okay, right. So what I want to highlight to you is this. Now T, note that T is very much smaller, very much smaller than A. Right, you can see for yourself. This is our thickness, and that is our A. So the magnitude is very largely different. So when that's the case, this term can be approximately equal to what? 0. You can drop that term, right? Because T is very much smaller than A, right? So when that's the case, your IZZ, this is one thing you all have to take note, okay? For this analysis, is very typical, okay? So IZZ is equal to twice, right? So 1 over 12 plus by 9 over 4, or I just multiply them together. So 1 over 12 plus by 9 over 4 times 2 is equal to